Hello and welcome to our Physical Sciences session. My name is Temba. Today we shall be focusing our attention on a very exciting part of physics that has got a lot of practical implications. So what exactly are we looking at today? We're looking at internal resistance in the context of electric circuits. Right. Now, here's the mind map in terms of the concepts that have got to do with electric circuits. So what exactly are we looking at today? We're looking at internal resistance. So this internal resistance actually is in the context of electric circuits, right? And now there are a number of concepts that come into the understanding of what internal resistance is all about. That has a lot to do with terminal potential difference or terminal voltage. Okay, we can also think of it in terms of how EMF of a battery is affected by the resistance, as well as we talk about another type of voltage, which is the lost volts or the internal voltage inside a battery. But now these are some of the the ideas that need to come to mind. Right now, terminology, a very, very important aspect of our scientific language, because the science is embedded in a unique language. So when it comes to terminology, we immediately tempted to think about defining concepts, not just to define in terms of reciting them, but also with an intention to understand, right? So each time we talk of definitions, think about your remembering skills, your basic recall. These are your easy type of questions that we need to familiarize ourselves. It's all or nothing. The examination guideline becomes our source of reference in as far as how to define. So pay attention to the keywords in the definition, and also you need to use these keywords in the correct context. Right. So some of the terms I've indicated. We're going to talk a lot about EMF, okay, which is some form of voltage based on the source of energy, which is the battery. We'll talk about the lost volts. Pay attention to how lost has been written. Okay, it means that energy cannot be lost. It means there are some implications in as far as energy or work done per coulomb of charge. And then our core focus is based on internal resistance. Right. Now the big question that we want to ask ourselves is, what is internal resistance? We need to create an understanding of what internal resistance of a battery is all about. Okay, so the internal resistance is a resistance found inside the battery. Now the word internal suggests that this resistance is inside the source or the battery. So the symbol for internal resistance is small letter r, while we know that the uppercase R generally represents resistance as an electrical physical quantity. Right. Okay. Now here's a circuit diagram showing internal resistance of a battery. Now in a simple circuit, this is a closed circuit or a complete circuit. It means there is current in this circuit, provided the battery provides energy or it does work per coulomb of charge. Now, of particular interest to us is that resistance. So this resistance is actually inside the battery, right? Now, if you look at the light bulb, it has got its own resistance, capital letter R. So in terms of notation, each time we denote internal resistance of a battery, that is. So the moment we say internal resistance, we're talking about resistance inside the battery. So the symbol is small letter r, while resistance in the external circuit for any device or electrical component will be denoted by a capital letter R. So both small letter r and uppercase R denote resistance, but the distinction, or how do we distinguish between the two? The small letter r represents our internal resistance, which is found inside the battery. Right. So this is a general setup of a circuit. Okay. So inside the battery there is resistance. Now the resistor inside the battery offers resistance within the battery or within the source itself. Right. Very, very important. Okay, but pay attention that the internal resistance of the battery and the resistance of the light bulb are actually in series. So we can think of the total resistance in this circuit in terms of external and internal as R plus R. So this is the total resistance in the circuit, right? Now, the plus suggests that these two are actually in series, right? So in the context of this simple circuit, we are saying that whatever current passes through the internal resistor inside the battery is the same current that passes through the emitter as well as the light bulb. Hence, pay attention to the series arrangement between the external resistance and the internal resistance of the battery, right? So we go on and say the internal resistance of the battery can be treated like any other resistor in series. We've managed to arrive at that, okay? Hence the plus, okay? Right. And then here's a simple circuit that we've set up using a simulation, right? So this is our battery. If we can zoom our attention to that part of the circuit, that's our battery. So inside, this battery consists of two cells that are connected in series. But between these batteries, or inside this battery, there is that resistance, which is the internal resistance of the battery. Now, there is current passing through the battery, which is the same current. So how much current passes through the internal resistor? So the current that passes through the internal resistance of the battery in this case is equals to 1,12 amperes. But what's the current that passes through the light bulb, right? The current that passes through the light bulb is 1,12 amperes, right? Right. What is it that we note here? The amount of current passing through the battery or the internal resistor of the battery is equals to the current that passes through the light bulb. So what is it that we can deduce from that? The amount of current passing through the resistor inside the battery and the current passing through the light bulb is of equal magnitude. So it suggests that these two indeed are in series, because in a series combination of resistors, the amount of current remains constant. Right. This is a very, very important understanding to say that the resistor inside the battery and that of the light bulb are actually in series. Right. Okay. Now, the internal resistance of the battery is usually hidden. Look, if you look at a battery in real life, you don't see that component in terms of the internal resistance. So the internal resistance of the battery can not be measured directly because it's inside the battery. So a lot of chemical reactions take place inside the battery, and as a result, we appreciate that the battery has got its own internal resistance. Okay, but how can we show that? Okay, we have used this demonstration to show that inside this battery there is internal resistance. So in other words, we can safely say, okay, these are the terminals inside the battery, right? Then we've got that small resistor, okay, inside the battery. Okay, now these are cells that are connected in series. So within this battery, what happens is we've got the internal resistance. So we cannot see this in real life, but then how do we measure that? So if these two cells are connected in series as shown in the the circuit diagram to our right, we would realize that the same reading across the light bulb of 6,75 it's obtained. Similarly, if we put a resistor which is going to be the resistance, internal resistance of the battery, we obtain the same voltage across the light bulb. Okay, so in other words, suppose these are two 9-volt batteries, so the EMF reading in this case is equals to 18 volts for argument's sake. Suppose the internal resistance of each battery is equals to 5 ohms, right? So it means the total internal resistance offered by the battery, if each cell is 5 ohms, will give us what? 10 ohms, right? Okay. Now, the amount of current passing through the light bulb will be equal to the amount of current that passes through the battery, all right? So it says to us that in reality, this is the arrangement, but we are able to determine how much internal resistance is carried by that battery if each one of them has a resistance or internal resistance of 5 ohms. So each battery has an internal resistance of 5 ohms according to this setup. So these are some of the, this is a distinction of what exactly happens in reality in terms of how we understand internal resistance of a battery. Okay, so when current passes through any resistor, energy is dissipated per coulomb of charge. Right. So a light bulb essentially is a resistor. We want just to put that, out as clear as possible. But what does an electrical resistor do? It's any component that dissipates electrical energy to other forms. So in a light bulb, typically, what would you expect? You would actually realize that a certain amount of electrical energy is transformed to light. Okay, so that's what happens through a resistor. So inside the battery, the electrical energy that the battery can actually dissipate, some of it is transformed to heat energy. That's why inside the battery, we want to appreciate that there is some internal resistance. So there's a potential difference across the resistor. Okay, so if for argument's sake, this was the light bulb, pay attention, the big R represents the external resistance. Okay, so there is potential difference across the resistor, right? Okay, now how do we measure potential difference across the battery in a closed circuit? So this is a complete circuit. In other words, if you look at it in terms of the potential difference, 3 joules, 12 joules per coulomb of charge, it means that the V load in this case, or the external potential difference in this case is equals to 9 volts. Where does 9 volt come from? It comes from the difference between 12 and 3 joules per coulomb of charge. So 9 volts suggests that there is actually 9 joules per coulomb of charge. That's the amount of work done for every coulomb of charge. So it means, in other words, we've got 9 joules of work done for every coulomb of charge. That's our V load, or in other words, this is our V external, right? Okay, and then across the light bulb, we've got the same thing. The potential difference is equals to 9 joules per coulomb, right? Okay, so when current passes through the internal resistance of a battery, energy is transferred per unit charge. There is potential difference inside the battery. This is the 9 volts that we spoke about, okay? Right, and then we are saying that as work is done inside the battery, you'd realize that between 12 joules and 3 joules per coulomb of charge, the potential difference is actually 9 volts. That's why we connect this voltmeter between 2 points. So the amount of work done per coulomb of charge between these 2 points across the battery is equals to 9 volts, which is the same as the one that we get also across the light bulb. Okay, so this is our V load in as far as the closed circuit is concerned. But bear in mind that the same amount of current passes through each of these components. That's the ammeter, the battery, as well as the light bulb. Right, so what is this internal resistance? This is the potential difference inside the battery. It's also called the lost volts. Volts, are they lost? Because we know that voltage is work per coulomb of charge, so, or energy per coulomb of charge. So if we think of it in terms of energy, we know that energy cannot be created or destroyed. So our V internal is equals to the product of the current passing through the battery and the internal resistance of the battery, right? Okay, so the voltage is not actually lost. That's what we want to appreciate. It is just not available to the external circuit. Okay, right. So if by all means, in this case, this battery provides a V load of 9 volts, it means what is available for the external, in this case, is equals to 9 volts, okay, which is our V load. So, okay, so the internal resistance of the battery can be treated just like any resistor in series, because the same amount of current passes through the battery is the one that goes through the external circuit. So we add up the voltages in the external circuit and the internal circuit. What does this give us? It actually gives us that this is the maximum reading, which is the EMF, is equals to V load plus the internal resistance. So this becomes the maximum reading. Okay, so according to Ohm's law, we know that voltage is the product of current and resistance. So this is our V external, while that's our V internal. It gives us the maximum voltage, which is equal to the EMF. But then the EMF reading is the one that is measured across the battery while the circuit is open. Right, okay. So these are some of the very important concepts around, EMF, around internal resistance. We'll take a short break for now. When we come back, we'll look at more on the actual measurement and, quantifying or determining internal resistance of a battery in an electric circuit. Let's take a short breather for now.